Okay, sorry for the delay. I promised somebody to try and get a recording of this lecture, and I thought it was actually a nice experiment. So I got a very tiny camera, and let's see how that works. Of course, I'll make it available to all of you, and also if it all works, right? I'd like to know if this is valuable at all to you. Okay, we have to start with the tale of last week, because we did spend some time on the Hilbert system, but then there was a part of the intended material that I didn't get around to. So that has to do with resolution. So just to get everything back in your mind, we've dealt with one semantic method for establishing unsatisfiability of a formula. We have dealt with two syntactic deductive systems to establish validity of formulas, the Gentzen and Hilbert systems. Now finally, the last method I want to present to you, still for propositional logic, is another syntactic method, but this one is again for showing unsatisfiability of formulas. So the semantic flows we've seen, deductive systems we've seen. Now I'm going to talk about resolution. So what is resolution? Well, first thing that we need here is the so-called conjunctive normal form of a formula. You might have seen in the past the disjunctive normal form of formulas. Let me just ask. To whom does this mean something? When you say, yeah, normal form, that was the disjunctive or conjunct or any? Both? Yes? You too? Okay, so then maybe I can be brief, although not all hands were raised, so maybe I should not be too brief. But, well, first of all, the word normal form here means something. You can need the word normal form in more contexts. Normal form, in principle, means that any formula in this logic can be rewritten to an equivalent formula in normal form. And the word normal then means it is the norm, so it is something that you try to achieve. Rewritten, when I say rewritten, an equivalent, what is that equivalent going to be? How equivalent should formulas be? Yes, this is notion of logically equivalent, which, if you think back, means that two formulas have exactly the same sets of models, right? So by saying that we have a normal form, we are claiming that any formula in this logic has an equivalent formula in this normal form. And in fact, for the conjunctive normal form, there's a fairly straightforward way to actually get there. But first, let me define it again. For those who haven't seen it, it's a conjunction of disjunctions of literals. So to start with the last word, a literal, what's that? A literal is either a proposition or a negated proposition. Then a disjunction of literals therefore means a lot of those with ors between. And a conjunction of disjunctions means a lot of those disjunctions with ands between. Okay, then maybe I can just ask you, maybe this is familiar enough for you to know this. How do you get from an arbitrary formula to one that is in conjunctive normal form? Can you think of a way? Please.
Well, first, probably just get from an arbitrary operator to just operators with ands and ors and nots.
So that's step one, convert operators to and, or, and not. Okay, yes?
The Morgan's laws?
Sorry?
The Morgan?
Okay, what do you want to use the Morgan's laws for?
To to get the unary operator on the propositions, not on the parentheses.
So the unary operator, you mean the negation, right?
The negation.
Yes. So you want to push the negation in, so to speak. That's right. So apply de Morgan's laws. This is not good enough. It's not going to be visible on video. Apply de Morgan's laws to push negation inwards. Yes, and then?
Something like double negation might occur. So
Yes, you might have double negations. Those are, of course, pretty easy to get rid of. Let me write it nevertheless. Get rid of negation on top of negation. So just remove both of them. Is there anything left? Are we done now? Yes, you have to do something with the ands and the ors, because you might now have a formula, for instance, that looks like P or Q and R, which is not in conjunctive normal form, and there might be deeper nestings of ands and ors, of course, right? So how do you get rid of those?
distributivity.
Yes, there are various distributivity laws that help you here. And essentially what we want, because of its conjunctive normal form, we want to lift all the conjunctions to the top, and the disjunctions can so stay below. And so it's apply distributivity. And that's all there is to it, essentially. And if you think of a formula as a tree, as I've encouraged you to do, then I think that you can see that this indeed will get, well, first you have to realize that you can indeed convert arbitrary operators to ands and ors and nots. We've seen that you can. Then you have to realize that these De Morgan laws are indeed powerful enough to push the negations all the way down in your tree. Here it says push inwards, but if you think of it as a tree, push it all the way down in the tree. And then, yeah, you might have double negations, those are pretty easy. Distributivity, yes, we have laws that allow you to pull the conjunctions up in the tree, and then you're done. So this is a mechanic process which computers actually are much better at than humans. And then the theorem, which makes it the normal form, is that for every formula, there is a formula in this conjunctive normal form, which is logically equivalent with the initial one. And now the next 2 slides, I think, or 1.5, are just about this construction. Should I do an example? Who would like to see an example of how this works? Yes, example? Okay, let's do one example. I think it might be on the next. Oh, I do have, actually here, this slide has some terminology which is going to be important. Because such a conjunctive normal form, again, is an and over lots of ors. A clause will be the or part. Every set of literals with ors between is going to be called a clause. And you can, of course, make this just a set. You can just say, I take the set of those literals, and I want to interpret it disjunctively. Then a clausal form formula will be a set of such sets. So I deal with these formulas as if they were sets of literals. It's not really different, but it allows me to formulate the notion of resolution a bit more handily. Okay, so here are examples of a clausal conjunctive normal form formula. This would be the corresponding clausal form. Yeah, you see a set of sets of literals. Each of these inner sets actually were disjunctions of literals. And then, just to be as a syntactically handy notation, you can write this down even shorter by taking all of these sets, not putting all the brackets and commas there, but just giving it as a string of literals and putting the negation as a bar on top. Still the same thing, but a much more convenient to write. Okay, this is the procedure, and here's an example. Let's just go and do the example. This is not an interesting example. I'll do another example, because this one already has the negation all the way inside. It's not as interesting as it could be. So let's do, I don't know, the negation of that formula. Not P implies Q, implies not Q, implies not P.
Don't you actually,
Yes?
don't you actually get not outside because of the definition of the implied operator?
True enough. Okay, yes. So maybe the example as it is there is actually more interesting than this version. Okay, so the 4 steps are now gone from the whiteboard, but I'm sure you still remember them. First step was convert all the operators to and, or, and not. So you already said it. Converting this implication means you put an or there, and you get a not over the first operand. So it's like this. And then you get the second operand, which is not Q implies P. That's one. We just got rid of one operator. Peter.
So it should be not be.
Yeah, true.
The last one.
This one should be not, right?
Yeah, but the last one should be.
Oh, and this. Oh, I copied it wrong. Yeah, thanks. And this is nonsense. So, I'm glad that you are awake.